Welcome once again to our online classes, and today we are going to look at chromatography, the theory of chromatography. Imagine you have a mixture of components, let's say like an ink. Then you need to ensure that you separate them into individual inks. So what are you going to do? You must look for a technique that you can use to separate this ink, and then you identify that, okay, this is a red ink, this is blue ink, and this is a white ink if there's one that exists, or this is a black ink. So one of the techniques that you can use in that case is chromatography. So when we talk of chromatography, it's a separation technique, or it's a technique that we can use to separate, identify, and determine different components within a mixture. Now, you can have a mixture that has different components, of course, and these different components move or migrate from point A to point B at different times. So because they move at different times, then it means that if you put them all together at point A and then they move at point B, towards point B, it means that at, let's say, t is equal to 1, A has reached at point B. T is equal to 2, B has reached at point B. And when t is equal to 3, then C will have reached at point B. So it tells because they have a different migration rate, and this different migration rate is because they have different chemical properties that makes them interact mostly within that environment, that makes some to spend more time and others to spend less time. So during that different migration rates, that's when separation is done. We have what is called the stationary phase, sometimes denoted as SP, and we have what is called the mobile phase, sometimes denoted as MP. So now, what is a stationary phase? In a layman language, stationary phase is a phase that is put within a column that doesn't move. From the word stationary, it's just a phase which is there, and it is this through phase that we can force our mobile phase to pass through it. Mobile phase is a phase that passes through the stationary phase. Mobile phase is the phase that passes through the stationary phase as it carries the analytes or solutes or a mixture from one point to another. So we normally are going to talk about these two phases, the mobile phase and the stationary phase. Now, for separation to take place, meaning that the chemical nature or chemical properties of the stationary phase and the mobile phase must be different. So you may find that the stationary phase is polar and the mobile phase is non-polar, or the mobile phase can be non-polar and the stationary phase is polar. And it's these differences in chemical properties between the stationary phase and the mobile phase that is going to allow the separation to take place. Why? Because during this interaction, some of the components within the mixture will find themselves more attracted to the stationary phase, while others are going to find themselves more attracted to the mobile phase. So it is during that interaction that can bring about the separation. Now, the process in which the mobile phase carries components of a mixture from one point to another is what we call elution. So elution is the washing away or washing down of components of a mixture from one point to another. And then if I was to draw, for example, a column, let's say this is our column chromatography, okay? So, and here is the point. So let's say the red one is the stationary phase, let's say silica, and then we introduce inside this mobile phase, of course, and introduce our mixture A plus B plus C inside here. Then they are going to be washed down through elution. We have said that elution, so they are going to be eluded, and when they reach here, we are going to collect the solvent. So the solvent that we collect from the column, the solvent that comes out of the column, is what we call the eluate. That solvent or mobile phase that exits the column, we call it eluate. But the solvent that we use to carry the mixture or we use to carry the solute is what we call the eluent. So most of the time we're gonna say stationary phase, mobile phase, or eluate, elution, eluent, those words. So make sure you get used to them. So in our next slide, remember we said that chromatography is a separation techniques that use to separate components within a mixture based on their migration rates. Okay, so let's look at this slide. If this is at t is equal to 0, t is equal to 0, a at t is equal to 1, t is equal to 2, t is equal to 3, and t here is equal to 4. T is equal to 4. Let's look at when t is equal to 0. At this point, we have just introduced our sample at this point, and our sample is a mixture of A and B. Okay. Now, at t is equal to 0, all of the mixture, all the components of a mixture is at the same point. And remember, this is our detector. So we are going to see which component in the mixture between A and B is going to reach to the detector first. And why is it going to reach at the detector first? Now, at t is equal to 1, you can see that when we introduce the mobile phase, then the mobile phase pushes or washes away the components of the mixture until at this point you can see A has moved ahead than B. However, there's still no proper separation between A and B, but at least at t is equal to 1, the separation has started to appear a little bit. At t is equal to 2, in this part here, when t is equal to 2, you can see that A has separated. There's at least separation between A and B, such that you can even see a clear distinction between A and B and the stationary phase between them. Now, because now you can start to realize that A is moving faster than B, it means that A is going to reach to the detector before B reaches, and therefore A is going to be detected first before B. And that is why now, as time goes by, we continue to introduce mobile phase. Then A at t is equal to 3, A reaches the detector first, and once it reaches the detector convert those signals into a readable outputs or printable, what we call the chromatograms that we are going to use to interpret the data. So once A has reached at the detector, it is being detected, and then a peak of A will be shown in the chromatogram, and then B come out later at t is equal to 4. Now, you have realized that now A and B have different affinities, or they are moving at different rates within the same color, within the same mobile phase. However, A reaches the detector faster than B. So it tells you that B is lagging behind while A is moving faster. So B is lagging behind. It means that the polarity of B and the polarity of the stationary phase is somehow closer to each other, or are somehow the same or similar, while the polarity of or the chemical properties of A and the mobile phase is almost the same, and that is why A finds itself in the mobile phase than B. I hope that makes sense, and that is why now we are going to introduce a certain word called retention time, and that's why you can see that A reaches the detector faster than B, because A was moved within the mobile phase faster than B. And you can see that at t is equal to 0, no separation, t is equal to 1, 2, there's no separation, but t is equal to 3, there's a separation. So you can see, you can draw here, and then you can see the time separation took place. Okay, that's the time separation took place. So you can see here we're going to introduce terms like column resolution, column efficiency, and you can see here there's a better column efficiency because there's a better better separation. Now if we were to draw, remember we introduced them at t is equal to 0, so that between this time until, let me put it here, until this time, this one we call it tr of a, and from the same point here until this one here on the top here, that is what we call trb. Tr simply is the retention time. We are going to look at it. So retention time is the time the sample take or the solute takes from the time you inject it or you introduce it here until the time it is detected at the detector. Okay, retention time, like how much time did the solute spend within the column from the time you introduce it until the time it entered into the detector or time detected. Sometimes you can say just the total time the solute spends in the mobile phase and the or stationary phase. And the retention time can also tell us, we're gonna talk about that. Now, let's continue with the theory of chromatography. We have what is called the distribution constant. Now, with the distribution constant within that column, you remember within that column, we have A and B. So we can say that the activity of A and the activity of B. Now, in terms of the molar concentration, we can then call this distribution, or we can represent distribution constants as Kc. This is what is happening. You have solute A and solute B within a mixture. You may find that solute A spends more time in the stationary phase, unlike it spends time in this mobile phase, when the mobile phase and the stationary phase is at equilibrium. So we can say then the distribution constant Kc could be the activity of solute A in the stationary phase over the activity of solute B in the, of the same solute A, activity of the solute A in the mobile phase. So we look at one solute at a time. So here we have two solutes, but we're going to focus on A. So we have solute A. How long does it spend time in the stationary phase and how it spends time in the mobile phase? So because it is an activity, we are going to look how much of it is in the stationary phase relative to how much of it in the mobile phase, when stationary phase and mobile phase is trying to be at equilibrium. Now we can represent this in terms of concentration, and we can say that, okay, the molar activity in terms of concentration can be concentration of solute A in the stationary phase over, compared to its concentration, the same solute A in the mobile phase. Now, distribution constant can tell us something, so we can go ahead and calculate the concentration distribution constant and say that, look, if let's say the molar concentration of the solute in the stationary phase is 5, for example, and in the mobile phase it is 2 molar concentration, and then we can calculate our Kc, and in this our case, Kc is going to be 5 divided by 2, that's going to be 2.5. And in the case whereby our Kc, which is Cs over Cm, is equal to, let's say now, our Cs, the molar concentration of solute in stationary phase is 3, while the molar concentration of solute A in the mobile phase is 5, that's going to give us a Kc value of 0.6. So if you check in scenario A, I'll call this scenario A, scenario 2, and this is scenario A, Kc in scenario A. So if you check Kc of scenario A, we have the Kc value of 2.5, and the Kc of scenario B, we have Kc value of 0.6. So in the second part, the Kc value is smaller compared to the Kc value in scenario A. Why? Because if we check the molar concentration of solute in the stationary phase is higher compared to its concentration in the mobile phase. While in B, the molar concentration of the solute in the stationary phase is smaller compared to the its molar concentration in the mobile phase. And when you compare these two, you can see just by calculating the Kc value or the distribution constants, there's one thing that you can deduce or you can make an assumption from that. Now, when you calculate a Kc value and you find that it is large, it tells you that the molar concentration of the solute in the stationary phase is larger or is higher compared to its molar concentration in the mobile phase, and the vice versa is true. So that's what we call the distribution constant. We have also what is called retention time. Of course, we have said that retention time is the time taken for the sample to move from injection time or the time you introduce it until the time it gets out. Now, we have factors that can affect the retention time. It can be affected by temperature, or flow rates, and nature of the stationary phase or the mobile phase. Let's look at the temperature. How does the temperature affect retention time? Remember, retention time is the time it takes solute to move from the time you introduce it to the column until it gets out, okay? Or until it gets detected by the detector. So now, let's take an example of a mobile phase which is a gas, okay? If the mobile phase is a gas, if you increase the temperature of a mobile phase which is a gas, and we know increasing the temperature increases the particle of a gas. So it means that when you increase the temperature of a mobile phase, the mobile phase is going to move faster. And in that case, for example, in GC gas chromatography, you are going to reduce the retention time, because if you increase the temperature, you are going to make the mobile phase, which is a gas in this case, to move faster, and therefore whatever is being carried by the mobile phase is going to spend less time within the column, and therefore increasing the temperature of a mobile phase, you are going to reduce the retention time, and therefore the solute will spend less time in the column before it gets detected. And when it comes to liquid chromatography, whereby the mobile phase is a liquid, now if you increase the temperature of a liquid, you are breaking the intermolecular forces like the hydrogen London dispersion forces within that liquid, and therefore you are going to reduce the viscosity. Remember, viscosity is the resistance to flowage of a liquid particles, for example. So it means that if you increase the temperature, you are going to break down the molecules or the intermolecular forces within this molecule or this substance, in this case liquid mobile phase, and you are going to make it now move faster. So if you increase the temperature, you are reducing the viscosity, and therefore they are going to move faster. Nature of the stationary phase and the mobile phase, it is either polar or non-polar, and if the mobile phase is polar, and it means that the stationary phase should be non-polar. And if you have, let's say now you have a polar stationary phase, if you have a polar stationary phase and you have a non-polar mobile phase, if in the mixture you have a non-polar components, then they are going to be attracted more to a non-polar mobile phase, and then they will move faster. And the vice versa is true. So that's how temperature, flow, or temperature, nature of the stationary phase affects it. Let's look at the flow rates. If the flow rate is faster or high, meaning that the mobile phase will move faster, and the retention time is going to be reduced, because retention time, remember, is the time they spend within the column, okay? So if their mobile phase is moving faster, it means that they spend less time in the column, and when they spend less time in the column, it means that the retention time is being reduced. The time they spend in the column is being reduced. So increasing the flow rate of the mobile phase reduces the retention time, and reducing the flow rate, if you reduce the flow rate of the mobile phase, it means that the mobile phase is going to spend more time to flow from point A to point B, making the solute particles to spend more time in the column. And then we have what is called the retention factor. Now, when it comes to retention factor, which is represented by the letter K, retention factor is simply the time a solute spends in the stationary phase compared to the time it spends on the mobile phase. Let's take an example. If we could just say TR of B, let's say TR of solute A in the stationary phase compared to TR retention time of, or we can just simply say of A in the stationary phase over the mobile phase. So now a retention factor K can tell you Column efficiency, and it can also tell you the nature of the components that you are trying to separate. If the retention time in the stationary phase is higher than in the mobile phase, it tells you that that solute was spending and interacting more with the stationary phase than the mobile phase, and that means that that solute particle has same polarity as the polarity of the stationary phase. And if the stationary phase, if the retention factor if the solute spend more time in the mobile phase, unlike in the stationary phase, it tells you that that solute has similar chemical properties, or almost, in this case we're going to talk of polarity of the solute is more similar in the mobile phase, and that is why it was spending more time in the mobile phase. And we have the selectivity factor. Now, when it comes to selectivity factor, it's just going to tell us the ratio of the distribution constants of the more retained species compared to less retained species. When we are talking about retained species, it tells us that these are the species that spend more time in the stationary phase, unlike they spend time in the mobile phase. So now, selectivity factor, let me just wrap quickly. So this B is the more retained species and A is the less retained species. Factor can tell us things like column efficiency, column resolutions, and things like that, and how separations can take place. Now, to understand these two words, band broadening and column efficiency simply means the ability of the chromatogram to provide the best fit, or to provide high quality separations that does not have broader peaks, separations that give you a better chromatograms and high quality peaks. That is what column efficiency is. Now, band broadening takes place when you have, or is the quality of a column to provide poor peaks or low quality peaks, because the bands, during separations you have large or lagging solutes spending more time either in the stationary phase and creating that broadness of the peak. Now, when it comes to band broadening and column efficiency, we normally introduce these two ones, or this electrical calculation. So we have what is called N, which is the number of theoretical plates, which will be equivalent to the length of the column divided by the plate height. So number of theoretical plates N, you can see that N, number of theoretical plates, is directly proportional to the length of the column, and it is inversely proportional to the plate height. Now, N is simply the number of steps. In physical chemistry, in phase changes or physical chemistry, we define theoretical plates as the number of occurring steps. So the more steps you have, the better separation is going to take place, and that one you can see is dependent on the length of the column. So it tells you that if you have a longer column, you are going to have a proper separation because of the more number of theoretical plates, while if you have a smaller plate height, you are going to have high number of theoretical plates, and if you have a longer plate height, then you are going to have a smaller number of theoretical plates, and that's going to give us low efficiency. So plate height is sometimes what is written as this H is sometimes written as plate height equivalent theoretical plates, HEPT, or theoretical plates. Sometimes we write it at some plate height equivalent theoretical plates. So now this is what is happening. You have a number of theoretical plates and the length of the column. If you have a longer column length, you are going to have more theoretical plates. Let's say this is the column length. This is just the column length, and then you also have this column here, very shorter one. So by look of things, you may think that because this is column B and this column A. So if you look at column A, it will take more time to move from here to here, going to give us more number of theoretical plates, and in that case you are going to have proper separation technique. Proper separation that is going to give you high column efficiency. But if you just in B, you just put the mobile face, and after a few time or after a few minutes, the detector has detected the analyte within a short period of time. And in A, the peaks could be like this, for example, proper separation, while in B you can have a peaks which looks like this, okay, because there was no proper time for them to separate properly. So in this case you can have low column efficiency, while in A you can have high column efficiency. So this is what happens. Now the number of theoretical plates, okay, let's say this is our chromatogram, and I just want to use an example. Okay, I'll just try. Okay, so let's say okay, so let's say this is our A and this is our B. Now it tells you that A is the one which is first detected and then B is detected. But if you look carefully, there is peak here. So from here to this point we call it TM, or what we call the void time. Okay, void time. So it's the time of the unretained species. What is unretained species? Unretained species are the species that does not interact with the stationary phase. So there are the species that are in the mobile phase. Immediately you introduce the mobile phase, they go quickly and they're the first one to be detected. So do not confuse this as a peak. This is as a peak of the analyte. This is the peak of the unretained species, meaning that the species that were not interacting with the stationary phase, they were only acting with the mobile phase. Then now from the same time until this point here, this is the TR of A, and then from the same point until this point here, look, it is not this, it has to be at the apex here. This is what we call TR of B, retention time of B. So in this case, A was detected first, then B was detected earlier. So this number of theoretical plates, we can also find it, and just by saying our number of theoretical plates is equal to 16, or TR, let's say we want to calculate for A, TR of A over width of A, then we square it. Okay, so now you take the ruler and you measure the distance between here and here, then you look at the scale that is given. Maybe the tension time is given in seconds, then you will measure that, you will have the tension time of A. So that one you are looking for number of theoretical plates of A. And then the question is, how are you going to get the width of A? So this is what you do. For the width of A, you will come here, and then you'll draw a line which is tangent. It is not that straight. okay, and then you come also this side, okay, you put a ruler like this, then the distance between this point and this point, this is the width of A. You do the same for B, and then you do the same for B, and this is the width for B. So let's say this is 7, let's say this is 7.0 and this is 2.6, then our NA is going to be 16 into tension time, we say is 0.7.0 over 2.6 squared. You are going to do that also for B, and retention time for B is going to help you to get number of theoretical plates for B, which is going to be 16 TR of B over width of B and everything here squared. And then in that case you can get the average number of theoretical plates, which you can then say average number of theoretical plates will be NA plus NB divided by 2, the average of the two. Then from here you can calculate the length of the column by just saying, or you can calculate H by saying H is equal to L over N. Okay, if you want to calculate the plate height, or sometimes you can calculate H by saying it is the standard deviation squared divided by L. So this is how sometimes you can calculate our H. Okay, having said that, let's look at the next thing. So now let's look at the variables affecting Colunm efficiency. We have talked about Colunm efficiency as the ability of a chromatogram to produce a better high quality peaks. Okay, so I want you to pay more attention here. Look, this is liquid chromatography for A, and this is gas chromatography. So A is a picture for liquid chromatography and B is a picture for gas chromatography. So if you look at the plate height for liquid chromatography, it is all of them are in centimeter, but look on the y-axis you have dimension in 0.001, 0.002, while in the gas chromatography you have plate height in 0.02, 0.04. And then in the y-axis is the flow rates, and the flow rate is measured in centimeters per second, and here you can see 0.2, 0.4, 0.6, so a difference of 0. While if we look at the flow rate in gas chromatography, we have 0, 20, 40, 60, 80, and 100. So it's much larger. I want you to pay more attention. Compare the plate height in liquid chromatography and gas chromatography. You are going to find that the plate height in liquid chromatography is smaller than plate height in gas chromatography. Look at the flow rate. The flow rate in liquid chromatography is almost 10 times in the magnitudes lower than that one of gas chromatography. So gas chromatography has a higher flow rate than liquid chromatography, and I'm going to explain that why. So if you look at the plate height of liquid chromatography is way smaller compared to the plate height of GC. Okay, now with the plate, we normally remember we have said that N is equal to L over H. Okay, now this tells you that if you have a low value of the plate height, okay, if the plate height goes down, then the number of theoretical plates is going to go up, meaning that the length of the column is going to go up. Okay, and in that case we expect liquid chromatography, because its plate height is very small, we expect it to have a higher efficiency compared to GC, all right, because it has smaller plate height. When the plate height goes down, the number of theoretical goes high, because the number of theoretical plate is also directly proportional to L, so it means that we expect it to be high. However, it's very funny that in liquid chromatography the plate height cannot reach into 20 centimeter or even 30 centimeter. It is so small that it doesn't make any significance. Okay, it doesn't make any significance, especially when comparing the two. Now look at this one, the minimal here. I'm going to explain this. Minimal is due to longitudinal diffusion. So if you look at the minimal H, or the lowest plate height, the minimal H in liquid chromatography is around 0.02, while the minimal H in gas chromatography in GC is around 0.05. So a minimal in LC is much lower than a minimal in GC. So a minimal in LC takes place at a lower flow rate compared to a minimal in GC, which take place at a fast or a larger flow rate. So due to pressure drops, this plate height in liquid chromatography, it doesn't bring a significant, it's not significant when we are looking at the plate height and the flow rate of the solvent, or the flow rate in the column when the separation takes place, unlike in GC whereby the flow rate is high. Now the initial decrease in both we have said is due to longitudinal diffusion. Now why is that the gas chromatography has a larger or a higher flow rates compared to liquid? Look, in gas chromatography, we know that gas particles are far apart from each other, unlike liquid particles. And in GC, we use the injector port, so it means that it needs to be heated. So when you increase the temperature in the two, you'll find that in gas chromatography, the temperature is going to increase the movement of the gas particles, and therefore they're going to diffuse and move faster compared to in liquid chromatography. So if you look also, the length of column of the GC is about 50 meters to around 100 meters, while the length of a column in LC in liquid chromatography is about 25 centimeter. And due to that, the pressure drops there will not make it efficient compared to GC, which has 50 meters column length, 50 meters and above. Look at a soccer pitch, a football pitch, half of a soccer pitch. That one can be a length of a GC column. So it tells you that, okay, GC column length is long, and when it is long, it means that we have high number of theoretical plates, and therefore if the number of theoretical plates goes up, then the plate height is going to go down. However, if you look, the plate height of GC is way larger than plate height of LC. By looking at these two graphs, we expect LC to have higher separation than, or efficient separation than GC because of the plate height, right? That's what we expect. That it is contradictory because of the length of the column in LC, which is very small. And if the length of the column is very small, meaning that it's going to have low number of theoretical plates, even if the plate height is very small, then the separation is not going to be as efficient as it will be in GC, which has longer column length, meaning that there are more number of theoretical plates. So even if the plate height is a little bit big, but because of the effect of the length of the column, which is big, it's going to make it to have more number of theoretical plates, and it's going to increase column efficiency. Now let's look at what is called the Van Deempter equation. So Van Deempter equation helps us to check about the column efficiency and the separation. So H is the plate height, and A is the multiple path terms or eddy diffusion. This one we call eddy diffusion, and B term is what we call longitudinal diffusion, and Cu is the mass transfer terms. I'm going to explain one by one and how they affect the column efficiency. Okay, so let's start with A. A is the multiple path terms or eddy diffusions. So imagine here is a column. Okay, here is a column, or let's say we have particle A and particle B. So A is going to move like this. Imagine moving like this, while B is just simply moving straight. So B is having a lesser path terms, okay, unlike A. So you're gonna find that A is dwindling, is meandering around, taking more time. So when it takes more times when a solute or uses a long path or several paths to reach the detector, it is going to increase band broadening. So we are going to have band broadening, and that's going to cause low column efficiency. It is going to produce low column efficiency, and therefore the peaks are not going to be as efficient as they are. While B here is going to have a proper separation because B spends less time. It has its paths is very small. Okay, it's very small, so it's kind of going straight. So in B we are going to reduce the diffusion. Remember, we call it eddy diffusion. So even A, let's call this pool A. Let's say we have pool A and another pool A. So you'll find that there will be a diffusion between one pool to another as it navigates different path terms, and that's going to make that solute to lag behind. While in B, there are less pools, so it will just try to go straight, and as it goes straight, it's going to reduce the diffusion, and therefore when the diffusion is reduced, eddy diffusion is reduced, we are preventing band broadening or zone broadening, and therefore we are going to increase column efficiency. B, longitudinal diffusion. So I want to draw this as a column. So now if you look between column A and column B, this is the solute concentration. So what is diffusion? Diffusion is the movement of particles or solute particles from where they are highly concentrated to where they are lowly concentrated. Okay, so now if you have solutes which are highly concentrated at the center of the column, they will, let's say here is X and this is Y. At the center of column is X and at the edge of the column is Y. So as they move down, they will need to move towards where they are lowly concentrated. Okay, and if you look at this column diameter is bigger than this column diameter. So you find that in A, longitudinal diffusion will be more prolonged or more evident than in B. So longitudinal diffusion is just the movement of the solute particles from the center of the column where they are highly concentrated to the edges of the column or to other parts of the column where they are lowly concentrated. So as they move towards, as they spread out, as the solute particles spread out, they are going to spend more time within the column, and that is going to make them reach at the detector at different time, and that's going to cause what is called zone broadening. So it means here that longitudinal diffusion can also be a function of the column diameter. So if you have a huge column diameter like in A, longitudinal diffusion is going to be more pronounced than if you have a small column diameter like in B. Even in B, the longitudinal diffusion will still take place, but it will take smaller time, unlike in A. So that's how longitudinal cause or affect column efficiency. How? As the solute spread out from the center of the column to other edge of the column is going to increase band broadening, and once you have the band broadening or zone broadening, then you are going to have low column efficiency. Now we have the mass transfer term. So we have what is called CSU and CMU. CSU means that the mass transfer term in stationary phase. So this CU is the mass transfer term. So this S is stationary phase and this M is the mobile phase. So then how do they affect or cause, how do they affect column efficiency? This is what happens. So remember, for the mass transfer term in stationary phase happens such that our solute particle moves into the stationary phase and it needs to get from the stationary phase back into the mobile phase. I hope we are together. So this stationary phase, the solute, if this is the center of the column and let's say this is the mobile phase, it needs to move from the mobile phase into the stationary phase, spend some time there, and then move back to the mobile phase so that it can be washed down. So this is what happens. If the stationary phase is made up of thick particle, so it means that it will spend more time to penetrate into the stationary phase, and then even when it is coming out, it will spend more time. Or if the solute particle has stronger affinity to the stationary phase, it will get stuck there. It will be adsorbed, for example, adsorbed there, and it will, because it has stronger affinity, they will spend more time there before they come back to the mobile phase. And through that, we are going to create zone broadening, and it's going to be more retained, and through that we may not have proper separation, and we are going to have low Colunm efficiency. So the higher mass transfer term into the in and out of the stationary phase can affect Colunm resolution. And then we have mass transfer term into the mobile phase. You may ask yourself, we have the mobile phase, but how comes we're saying mass transfer into the mobile phase? So let's say that our packing particles are made up of several particles. So we have big, small, big, small. So this one are going to create spools of mobile phase. So we have our bigger mobile phase moving as we go down. I'm bad in drawing. So as it moves down, so it has to spread in this pool, this pool, this pool. So there are pools or collections of mobile phase due to the particle size, okay? Packing particle size of the material, or the packing material, or the different particle size of the packing material. So you will find that the mobile phase will diffuse from, let's say, from the center of the column into this another mobile phase, into this another mobile phase, into this another mobile phase. So during that mass transfer of the mobile phase or of the solute within the mobile phase from one pool to another pool to another pool. So if you have many pools within the same column, then you find that your solute is going to spend more time or a lot of time within the column before they get separated, and through that you can have low Colunm efficiency. The separation of the peaks may come up to like this, okay, or something like this, or something like this, okay, due to those mass transfer terms. And that's how these things affect. So this is called Van Deempter equation. Sometimes you can be told, write Van Deempter equation. Maybe write Van Deempter equation, you write it, and you are told explain how each term, or explain each term in Van Deempter equation in relation to Colunm efficiency. So you explain eddy diffusion and how it contributes to Colunm efficiency, longitudinal diffusion and how it contributes to Colunm efficiency, and mass transfer term. So mass transfer term, you need to put it into mass transfer term in stationary phase and mass transfer term in the mobile phase, and how they contribute to Colunm resolution and band broadening. So let's still looking at the variables affecting Colunm efficiency. Let's look at the particle size, okay? So the smaller the particle size, the higher the efficiency, because it's going to reduce diffusion distance like eddy diffusion and mass transfer terms. So remember, in the previous slide, we have talked about that the particle size, you can have particle size like this, okay? So you can have particle size like that, okay? Let's say another one here, okay? And then you are creating several path terms in the sense that the mobile phase is coming here, it can either choose this one here, okay? And if you have smaller particle size, so you can find that it's just moving like this. So this is B and this is A. So you can see in A, the smaller the particle size are, the higher the efficiency. Why? Because the eddy diffusion will be reduced, okay? While if you have larger particle size, it's going to create a longer and many path terms. So it's going to spend more time as it navigates. So as it spends more time to navigate, you are allowing diffusions to take place. And when the diffusion takes place, you are creating a good chance for zone broadening to occur. And once you have a good bigger zone broadening, meaning that the column efficiency is going to go down. Flow rate, we have talked about that. Low flow rates gives a low efficiency. If you have a low flow rate, like look, let's say this is the flow rate moving like this slowly, okay? It means that you are giving particles in that mobile phase to spread out, okay? But if it just move like this, boom, you are giving it, you are reducing the time from eddy diffusion to take place. Even longitudinal diffusion or eddy diffusion, any diffusion to take place. The question is then, so low flow rates, low column efficiency. Too much flow rates also creates to low efficiency. Why? Because it is not going to give enough time for separation to take place. So a better flow rate is a moderate flow rate, which will also depend on other parameters. So a better flow rate for a proper separation that leads to high column efficiency should be a moderate flow rate. And then column length, this one we have talked about. The longer the column length, the larger the number of theoretical plates, and this one can also give a higher efficiency. I know you're gonna say, but if the column length is long, is it not going to, the mobile phase going to take more time to move, and therefore it's going to allow diffusion to take place? Yes. However, as the longer the column length at a moderate flow rate, with the longer the column length, the more the number of theoretical plates, and at a moderate flow rates we are going to have more separations, because theoretical plate is a step. So one step leads to another step, leads to another step, and that's going to give us a better separation. Let's look at column temperature. So column temperature, if you have the higher the temperature, the better the column efficiency, because it's going to reduce viscosity. But if you are going to look at GC, it can also cause column degradation. Column degradation is when the column does not perform its work better. So we're going to look linear degradation, column degradation in the next class. Viscosity is the resistance to flowage of a liquid substance. So it means that when the liquid, especially in the LC, in the liquid chromatography, whereby the mobile phase is the liquid substance. So when the liquid is moving so slow, it means that it has high resistance. So if we have a mobile phase which is more viscous, it means that it's going to move slow, and it's going to enable the solute in that mobile phase to spread out, and it's going to allow zone broadening to occur. And if we have zone broadening occurring, meaning that the column efficiency is going to be low. Now, how does temperature make it better? If you increase the temperature of a viscous substance, you are going to break the intermolecular forces of that substance, and therefore they are now going to move faster. So if you increase the temperature, then you are going to allow the molecules, or you are going to reduce the viscosity, and therefore you are going to prevent eddy diffusion, any type of diffusion that can take place, and you are going to have a better column efficiency. Lastly, let's look at the methods of reducing band broadening. So let's look at the methods of reducing band broadening. Number one, we have for GC, decrease the temperature. So if you want to reduce band broadening, For GC, you are going to decrease the temperature. How? In GC, we are using gas chromatography, which is the mobile phase. If you increase the temperature, you are going to increase the particles of a gas, and they are going to move faster. So for GC, you are going to decrease the temperature. So if you decrease the temperature, meaning that you are going to lower the rate at which they are moving. Because remember, with the band broadening, if methods for reducing band broadening, you don't want it to be too slow. Actually, the temperature should also be moderate temperature, not even reducing it, moderate temperature, because if you decrease the temperature too low, then you are going to reduce the movement. So, and then in that case, you can increase even the thing. With liquid stationary phases, the thickness of the layer of the adsorbed liquid should be minimized, just like we said, especially for the CUS. If you remember CSU, mass transfer term to stationary phase. So we are saying that the thickness of the layer should be minimized. If you imagine you have this one, so it has to travel from here until here and then come back, and from here, if you have this thickness, so very small, it will spend less time in B unlike in A. So for liquid stationary phases, make sure that you reduce the thickness of this layer so that you can minimize band broadening. But if it is big, then you are going to increase band broadening. Now for packed columns, we have different columns. We have capillary columns and packed columns. For packed columns, band broadening is minimized by small particle diameters. Okay, when we talk of small particle diameters, we are looking at the packing size of the packing materials. So which is in this case at the stationary phase. So if the stationary phase has a larger particle size, meaning that in that case, so let me just make example. Remember the eddy diffusion. So if you have larger particles, meaning larger particle size of the packing material, in this case the stationary phase, you are going to, if they are large, you are going to have band broadening. Okay, but if you want to, because you are going to create multiple path terms, remember A in that Van Deempter equation. But if you have a smaller particle size, you are going to minimize band broadening because you are going to lower multiple path terms. For capillary columns, small columns diameter reduce band broadening. So we did show that because this is majorly going to reduce eddy diffusion, longitudinal diffusion. So if you have a column with a diameter of this size and a column of a diameter of this size, so this is the diameter of the column and this is the diameter of column B. This is column A and this is column B. So for A, you can see that it will travel that distance. It has to spread. It's going to spend more time, and like here, when it's going to spend less time. So with the capillary columns, make sure that you reduce the diameter, the column diameter, and for the packed columns, reduce the diameter of the packing materials. Okay, for liquid stationary phases, make sure that you reduce the thickness of the adsorbed stationary layers or the thickness, and for GC, decrease the temperature of the column, because remember the injector port, it works at different temperatures. So thank you so much for watching. We will continue in our part B, in which we are going to look at column resolution and other parts, and general illusion problem and some calculations. So methods for reducing band broadening. If you use this method, okay, then you can manipulate the same method to, if you are asked, explain factors leading to Colunm efficiency. Still here, you can use them, these factors, you can write them on the other side to show how they can lead to Colunm efficiency, high Colunm efficiency. If you are told of factors contributing to band broadening, still you use them. So depending on how the question comes, you use the same to talk on them. Okay, Thank you so much for watching. Bye.